In this video, we will discuss pixel transformations. We will review histograms, intensity transformations, thresholding, and simple segmentation. We will use OpenCV as it has all the functions. This video will only focus on grayscale images. Let's review histograms. A histogram counts the number of occurrences of a pixel, and it's a useful tool for understanding and manipulating images. Consider the following toy image with 3 intensity values. We can plot the occurrence of each pixel. We have 1 black pixel, 5 gray pixels, and 2 white pixels. Instead of counting the pixels, we can count the intensity values. Consider the following example as numbers ranging from 0 to 2, where 0 is black, 1 gray, and 2 is white. The histogram counts the pixel intensities. We represent these intensities as an array. The index of the array is the intensity level, R. In most images, we have 256 levels, representing the count of the different intensity of gray levels. Consider the following image. We can calculate the histogram as follows. We have the image, the channel we would like to calculate. In this video, we use the grayscale, the number of channels. Finally, we have the range of intensity values in yellow. We can plot the histogram as a bar graph. The darker portions represent the lower intensities. The brighter regions are mapped to the higher values. An intensity transformation changes an image 1 pixel at a time. Some image transformations depend on neighboring pixels. An intensity transformation T depends on only one single point, ij, in the image array, F. The image array F is converted to array G. The transform also operates on the intensity of gray levels R, mapping them to S. This changes the histogram. Let's apply a simple transform to a toy image. We apply the following linear transformation to the image array F, returning the array G. We apply the transform at the pixel located at the first row, first column. We get the following result at the same pixel location at array G. We apply the transform at the pixel located at the second row, first column. We get the following result at the same index in array G. We repeat the process for the entire array. Let's see how the transform changes the histogram. We have the histogram. Each pixel intensity is a function of R, or histogram R. The transform maps each intensity value at R to S. We have the new intensity values S and its histogram S. Let's see the relationship between histogram S and R. The value of histogram R has 1 intensity value at 0. When applying the transform to R, we see the intensity value of 0 is mapped to 1. The histogram S now has 1 intensity value at 1. We see the intensity value R equals 1 is mapped to 3. The histogram R has a value of 5 at R equals 1. In histogram S, the value of 5 is mapped to S equals 3. And so on. If we plot the histogram after applying the transform, we see the histogram is shifted and scaled. Image negatives is where we reverse the intensity levels of an image. Consider the following image. It's difficult to make out details. Applying the following transform will reverse the intensity levels of the image. We can apply the transform as an array operation as follows. The new image looks like this. We see the details are much more evident. The following plot shows the histogram. We can overlay the transform as a function of the intensity. The function maps the lower intensity values of 0, 1, and to 255, 254, and so on. We can plot the value of the histogram on the horizontal axis. We see this flips the histogram. A linear transform can be seen as applying brightness and contrast adjustments. We can use the following linear model, where alpha is simple contrast control and beta is simple brightness control. We can use the following values. Just changing beta, we can adjust the brightness. Rather than using array operations, we use the function convertScale ABS after applying the transformation. The function scales, calculates absolute values, so the intensity values fall in the 0 to 255 value range. We see the image is much brighter. We see the histogram of the bright image has shifted to the right. A lot of the intensity values have been mapped to the point value of 255. We can adjust alpha to change the contrast. We see the contrast in the darker areas have improved, but the lighter areas of the image appears washed out. Comparing the original image histogram to the histogram of the new image, we see the lower values exhibit more spread, but many of the larger values have been mapped to 255, explaining why the image appeared washed out. We can use nonlinear functions, but let's explore some algorithms that optimize contrast. Histogram equalization is an algorithm that uses the image's histogram to adjust contrast. Consider the following image with the following histogram. The function equalizeHist improves contrast by using the histogram to determine a transform that flattens the histogram. The resulting image has improved contrast. A threshold function applies a threshold to every pixel. It can be used in extracting objects from an image. This is called segmentation. The following function applies a threshold to the input array, input image array, input out, and outputs the result. The following portion of the code will cycle through each pixel, ij. If the pixel is greater than the threshold, it will set a pixel in the array image out pixel to some value, usually 1 or 255. Otherwise, it will set it to another value, usually 0. Let's do an example. Consider the following array. In this case, the threshold value is 1, and the min value is 0, and the max value 255. The first loop increments through the rows. For each column in input img, we check the condition. If the value is greater than 1, we set the corresponding element in image out to 255. Otherwise, we set it to zeros. We repeat the process for the second row. As none of the columns are less than 1, all the corresponding rows in image out is set to 0. We repeat the process for the final row. The result is all the values in the new image array are white or black. Consider the following image. It's histogram bimodal. We see the cameraman corresponds to the first mode. That is, intensities under 87. The second mode is the background. By setting the threshold accordingly, we can segment the cameraman. We use the function threshold to perform thresholding. The output new image is the image after thresholding has been applied. Along with the image ID, the input is the threshold, and the max value is set to 255. The final parameter is the threshold type. In this case, thresh binary. This means the output will be 0 or 255. In the output, we see the camera has 0 values, and most of the background has values of 255. We see the histogram intensities are mapped to black and white after thresholding has been applied. Sometimes it's difficult to select a threshold. Therefore, we can use OTSU method to select the value automatically. Ret is the threshold value determined. We see the image looks identical to the one using the manual threshold. Check out the lab for more.